Ready to go?
Yeah.
Okay.
Hi, everyone. Thank you all for coming. This is Ian. And I'm going to tell you about my thesis work of the last 5 years in boundary regularity for area minimizing currents. And I want to try to make this talk accessible, so please stop me. And advised by Camillo, who is here. So the setup is we study Plateau's problem, and Plateau's problem originally considers you put a wireframe into soapy water, and you get a soap film, which is spanning the wire. And in the simplest possible example, if you put a circular wireframe into soapy water, you get the disk, and this is what you see in this picture. And in a slightly more complicated example, you get the catenoid if you put two circles that are slightly separated. So the Plateau's problem, more in general, asks if I give you a boundary surface, find the surface that bounds this surface and has minimum area amongst all of the surfaces that are spanning this surface. This setup has a challenge, which is that if you only consider a class of smooth surfaces, you're not going to be able to solve this problem. And this challenge was overcome by Federer and Fleming in the 1960s because they considered a class of surfaces where this problem is solvable by compactness, because these surfaces are just weak enough so that they guarantee the existence of the solution in this class. So in a sense, they did solve the problem, but also what they did not do is tell us any structural properties about the solutions which are not just belonging to this class that this problem makes sense. Okay? So minimal surfaces or area minimizing currents, which will be what we consider in this talk, have a nice property that is not shared by every surface. And the nice property that is not shared by any surface is the monotonicity of this quantity, which is that if the surface is an m-dimensional surface, then the ratio of how much area you have on the wall of radius r with the corresponding power of r, this is a monotone quantity in r. And what this allows us to do is, this allows us to zoom in and tell us that if you zoom in, you are still going to get something in a limit which is still minimizing, but now it has more structure because it also has to be a cone. But there is a big problem that I will refer to later in this talk that I've studied, which is that this limiting cone might depend on the sequence. The reason that it's a cone is a consequence of this monotonicity formula, but the reason that this limit exists is just based on compactness by taking a subsequence. So in principle, even if I know that the limit has to be a plane, if I consider a spiral and I choose a spiral to be winding around in the right way, then I can have that this zooming in, these blow-up limits are going to be lines which depend on the sequence that you take. In some sequences, you don't have a limit. In some sequences, you have a line that is rotating. And I told you that the surfaces might become singular. So what a point is regular for a surface if this kind of weak class of area minimizing surfaces actually near this point agrees with a classical smooth surface up to an integral multiplicity. in codimension 1, so when the surface is 1 dimension less than the ambient space, the first example of a singularity is the Simon's cone, which is, if this is R4 and this is R4, is this cone. And this has a singularity at the origin, which means that at the origin you cannot represent it as a smooth classical embedded surface. That's also a minimal surface equation. And when the dimension of the ambient space is higher than 1 more than the dimension of the surface, there is a rich family of examples, which is those given by the zero sets of complex polynomials. And then an example here is for if you take in C times C, Z squared equal WQ, this is a 2-dimensional area minimizing current, and it has a singularity at the origin. And I will refer to this later. So how do we prove in general? What's a way of proving that something is area minimizing? So area minimizing, if it's something which is globally defined, if I have a surface which is defined in all the space, area minimizing means that if I take any ball and I try to replace the surface in this ball by something else, then the other thing that I replace it with, it needs to have at least the area of the surface. So if in codimension 1, so when the ambient space has one more dimension than the surface, if we have a very specific vector field which has these 3 properties, so this vector field will be adapted to the surface. So if it needs to be divergence free, it needs to have norm at most 1, and it actually extends the unit normal that defines the unit normal induced by the surface, then the surface is going to be area minimizing in the sense that I said. And how you prove this is if I make a change which is inside the ball, so I replace it by some other surface with the same boundary, then the divergence precondition, if you use the divergence theorem, will tell you that integrating will give you the same when you integrate this vector field dotted with the respective normals. And what will happen is that because of the third condition, the left-hand side is going to be equal to the area of the surface in this ball, and the right-hand side is going to be at most 1, because this vector field is almost 1. Okay? So this is if you can construct a vector field that has these properties, which is very non-trivial, and it really depends on the surface. I mean, like the third condition is the key condition that depends on the surface. Then you can ensure that the surface is going to be area minimizing. And I will come back later slightly to this. Is there any question about this? Yes. I think it depends on in some cases, I think yes, locally, I think it depends on the regularity, but I don't remember.
It's only, I mean, in codimension 1, you have a graph that amount of branches on the left.
Yeah.
So in higher codimension, functions.
So okay, so I gave you the examples, and then I'm going to tell you about the corresponding sharp regularity theories that come with these examples. In codimension 1, the dimensional estimate that was contributed by many people is that the singular set, so the set of points that are not regular, needs to be of dimension at most m-7, where m is the dimension of the surface. In codimension at least 2, then the singular set needs to be of dimension at most m-2. And in both cases, in the threshold, you get that the singular set needs to be discrete. And in both settings, it has improving the rectifiability, which is an isometric structure of the singular set. In the codimension 1 setting, it was Utilian-Simon, and it was later reproved by Neighbor and Valtorta. Aaron is here, and it was the techniques are much more flexible and apply to a wider variety of problems. And in the higher codimension setting, it was done by de Lellis, Minter, and Skorobotoa, and simultaneously by Kramel and Vikramasekera. And de Lellis, Minter, and Skorobotoa are using the approach that I will discuss later, which follows the same approach as Neighbor-Valtorta. So in some instances, we do the Allard has some nice theorems, which for some specific cases tell you that some points are regular. And the specific cases are, if you know that infinitesimally this density that I defined earlier is 1, then this is a regular point. And in the boundary setting, which is what I will consider, if you know that it's 1/2, then this point is a regular point. And in this setting, regular means no longer that it's a smooth surface in the sense that I described before, but now you also have a boundary. So it needs to be a smooth minimal surface that is attaching smoothly to the boundary. And a very nice theorem, which was actually even prior to Allard's boundary regularity in 1975, is that if the boundary has a convexity assumption, then every boundary point actually satisfies this hypothesis, and he proves that for every boundary point is regular for this setting. And the convex barrier assumption is actually simple to explain, which is that if you look at the tennis ball and you look at the white part of the tennis ball, the seam, this is in this picture it's a one-dimensional curve sitting in the two-dimensional sphere. So if Allard considers boundaries of this kind, so boundaries which are sitting in the boundary of an open convex set. So it doesn't need to be this two-dimensional sphere. It can actually be the sphere of dimension 1000, and his theorem will still apply. Then this will still be the convex barrier assumption. So what I consider, which generalizes the setting of Allard, is a higher multiplicity setting. So higher multiplicity means that the boundary, it means something like the picture. In the smooth case, it would mean something like the picture here, which is that maybe you have two smooth minimal surfaces attaching to the boundary. In this case, this boundary will be taken with multiplicity 2. There is also another possibility, which is that you can have, since we are considering oriented surfaces, the boundary can take multiplicity by a mechanism of cancellation between two parts. So in this case, is if you have a disk, or alternatively any smooth classical minimal surface, which has a boundary sitting inside, like this circle here. If you take, for example, this with multiplicity 1 and this with multiplicity 1, so that the orientations are appropriate. Now this with multiplicity 2 and this with multiplicity 1, so that the orientations are appropriate, then you will have some cancellation, which means that this boundary will be taken with multiplicity 1. And if you want higher multiplicity, you can take the multiplicity of this one and this one accordingly to generate that boundary multiplicity in this boundary part here. So these are two possible setups, and these two setups are setups that we consider regular. When we mean about taking a boundary, we mean taking a boundary in a weak sense of how it's defined in the class of currents. So we are actually solving this problem of minimizing the area with a boundary. And in this setting, you can also impose boundaries with higher multiplicity. So in principle, I don't tell you anything that the picture needs to look like either of these when I'm solving the problem. And the questions that I considered. So Allard already in 1969 asks, what can you say anything if you consider the same setting that he's considering, but replacing the multiplicity 1 with the higher boundary multiplicity? And then also Brian White, in a famous list of open problems, he asks about like, what can you say for the when you consider higher multiplicity boundaries in general? And here in codimension 1, the problem is fully solved in a sense, which is that there are no singular points. Every boundary point, no matter the boundary multiplicity, every boundary point, if the boundary is smooth, is a regular point. And here with regular, I mean the pictures as before. So if you're in codimension 1 and you're taking a smooth boundary, then you're only going to locally see one of these two pictures, where that picture possibly has multiplicity. Maybe that sheet has multiplicity 2, that sheet has multiplicity 1, and then the boundary is taken with multiplicity 3. Okay, so I'm going to tell you some more about the history of what has been done prior. So if the relevant parameters are the boundary multiplicity, the dimension, and the codimension. So before this n was 1 because the codimension was 1. But when you consider boundary multiplicity 1 and the codimension at least 2, then the best known result is that the boundary regular set is open and dense. And this is very different than the setting of codimension 1, where every boundary point had to be regular. And this is sharp in the Hausdorff dimension, because if you consider regularity as we defined, as I defined in a previous slide, then you can have a set of dimension 1 of singularities, of boundary singularities. Then in this other result of the Lellis-Narduli-Steinbruchel, they consider what happens with dimension 2, but they start to try to answer, they answer Allard's question of what happens when you put a convexity assumption. So if you put the convex barrier assumption, like in the tennis ball picture, then every boundary point is regular. And if you, then Narduli and Resende consider the problem again in dimension 2, but they remove the convex barrier assumption and they obtain the same analog as the theorem before. So if you see the slide, you would imagine that maybe the story is going towards every boundary point being regular for any dimension, which is not correct. And I will show this later. Yeah. So I mean sharp in the Hausdorff dimension, as in you cannot get a partial regularity saying that every point is of this type, of one of these two types, where there is only a single sheet, and this is with a multiplicity 1. So it is not a partial regularity statement that you can get in this context, because you can't get a singular set which is of dimension 1. So in this paper, in this paper of Camillo, Guido, Annalisa, and Jonas, they actually have an example in which of an area minimizing current, which is a flat half disk, and then a graph. So no, a flat disk, and then a graph. So it's like, wait, maybe. So there is a flat disk here, and then there is a half disk, which with a curve that is kind of like moving a lot. The touching set here is of dimension 1. This touching is a set of singularities. They are all crossing singularities, but you don't have a composition like I am telling you. Like you don't have at every point that the points where the surface is, you see the surface on both sides look like this. Does this make sense? So what I'm saying is that you cannot get the partial regularity theory which beats the full dimension, because there is an example in which if you define these points as this as the type of regular points, then you're not every point of these ones which is of dimension 1 is going to be singular. If you change your definition of being regular, then maybe you can say something. But if you don't allow, if for you this is an irregular example, then you're going to get the full the dimension is the full the dimension of the boundary. Okay, so I'm going to describe some of the ingredients that go into studying the problem. So when we study higher codimension, we need to use Almgren's multivalued functions. And the reason for using multivalued functions is that, as we like to do in geometric measure theory, if you don't want to destroy your problem by choosing bad parameterizations. So if you want, you shouldn't do things that include parameterizations which are too good if you don't know that they are too good at that point. So if at the starting point, we are not going to know if the surface is looking in a measure theoretic sense like 2 copies of a flat disk, so 2 copies of a disk inside a plane, then I wouldn't want to actually try to separate it into 2 classical single valued graphs, because this is going to introduce singularities because I put that parameterization which wasn't the best suited for the problem. So what Almgren then considers is he forgets he would parameterize this graph that is. So the picture will be if the disk is here, or maybe there is no. So if there are 2 things here, then when the dimension is higher, if you try to split it into two parts, you're going to introduce singularities. So then what you can do is you can say, okay, for every point here, there are 2 points in the above, and you can choose a function which is taking these 2 values above, but it's not caring about the order of the values. And this is the space of tuples that Almgren considers. And the right linear problem is minimizers of Dirichlet energy in this space. These functions generalize classical harmonic functions, but they are the right model to study a picture like this. Any questions? Okay, I guess I should. So I'm going to describe it in the linear setting so that some things get simpler. So the problem that I consider is I have a line, I have a half space here, and then I have a multivalued function which is taking 0 boundary value. So I have multiple sheets here, but they all collapse at the boundary. And the questions that you can ask are this function is an energy minimizing. It minimizes the Dirichlet energy as in the previous slide. And then the questions that one can ask are, if you look at the boundary point, are the blow-up limits unique? So if I zoom in at different sequences, do I always see the same pair of linear functions? If this, let's say this is multiplicity 2. So the question about blow-up limits is very closely related to the question of, is there a good sense of a normal derivative which can be defined as a multivalued function? And then once the regularity question would be, what does it mean for a point to be regular in this setting? And how large is the singular set? Okay, does this make sense? Any questions on the setup? So the first thing that I show is that the blow-up is unique. So I can actually define a multi-valued normal derivative, which is header continuous. And if in this setting, if we consider a boundary point to be regular, if we see the picture of that we like, which is two things that are separated and are harmonic functions, then in this setting, the singular set has Hausdorff dimension at most n-3, and it is rectifiable. And in dimension 3, it is countable. So I mean, like these are I'm just like I'm just this is just like a heuristic. Okay, no, I mean this is a heuristic. I mean, like my theorems are more general, but no, that sounds good. Yeah, this is in the multiplicity too. And okay, so the idea, the quick idea for the multiplicity 2 case is that, so I want to study what happens to these multi-valued minimizing functions, which are taking two values and are zero boundary value. But I want to study whether if I zoom in at different sequences, I see different things. So the way to do it is, at some point, if you look, if I know the following thing, that if at some point it looks close to a pair of linear functions, then it will need to get closer to a different pair of linear functions. Then this will tell me, by keeping track of this sequence, that this limit is actually the limit that I see, and it's not depending on the sequence. And does this make sense? So how you can prove a theorem like this is by contradiction. So you assume that it doesn't hold. And then what you're going to show is that you contradict the decay rate for harmonic functions to the first order approximation. But if you think of the pictures that I'm showing you, if I have something which looks like this, and then it does something which is very weird, then for me, this is going to be close to this pair of linear functions, but it's not going to be graphical here. So I do have to actually study to actually get these harmonic functions, I do have to parameterize on top of this pair of planes. So I do have to study the functions that are sitting here. And I do not have any hope of getting a parameterization that is extending close to the boundary. And somehow these functions that I'm using to study the problem are not defined close to the boundary. And this is introducing errors. And the way to control the errors, that I'm not going to go into detail, goes back to Leon Simon in 1993. and uses the remainder term of the monotonicity formula in a quantitative way. Okay, and this is the fun part that I'm hoping to get you everyone on board with, which is the example that I constructed. So I want an example of a boundary singularity for this problem. So what I consider is, I consider the unit cylinder in R3. And here, the problem that I consider is I consider minimizing functions with some boundary data. Okay, so I have this space of tuples, but what I'm doing is I'm solving in this weird space the Dirichlet problem. So it's something that is minimizing. It's a function. There is a function. So I'm considering a function U, which minimizes the Dirichlet energy, and in the boundary U restricted to the boundary of the cylinder is this function that I'm prescribing. So for me, the class of functions that we consider, this is all in the setting of multivariate functions. So the boundary value is taken by a function that is taking two values. But since I'm interested in the problem where the things are touching, it's important that in here is taking zeta boundary value. So I assume that the boundary data is of the form the vertical variable times some function which is a multivariate function. Okay, so in this bottom disk you're going to be getting two copies of 0. This is the class of problems that I consider, and what I want to show and what I will try to convince you is that for a problem like this, I can get an essential boundary singularity. And an essential boundary singularity is a point here where my function is not separating as two classical harmonic functions. So I don't care about crossing. So the picture is not really looking like a picture like this. And the picture is more looking like the complex square root, which is winding around and you cannot separate it into two parts. So if we actually take as a boundary value, let's say if this function xi is t times the complex square root on the other variables, so let's say if it's xi of t set is t times the square root of set, where this is taking two values, then what I can show is that the multi-value normal derivative is well defined in this disk. So I can make sense of a normal derivative, which is like gives me like a pair of linear functions for every point of here. And this is also true up to this boundary circle. Okay. So I do have all over here a function which is taking two values, which is the normal derivative. And something else that I show is that at the points in the circle, actually the function is regular. And what it actually means is that if it's really what you expect, which is that it's coming at an angle and you see two separate linear things at the level of the normal derivative. So what will then happen is that this multi-valued normal derivative at this boundary circle, it needs to agree with the function that I prescribed. Okay, So I prescribe t times the complex square root. So just based on the boundary value that I'm putting at this boundary circle, this normal derivative will need to be agree with the function that I'm prescribing. And what it means is that I'm seeing a function here whose normal derivative is Helder continuous as a multi-valued function, in particular continuous, but it's taking as a value the complex square root. I mean, like as a boundary value the complex square root. And if you know some topology, you will realize that this is not possible to do without an essential singularity. Because if every interior point here, so every boundary point in the interior of this disk was not an essential singularity, then it would need to decouple in a neighborhood as two separate functions. And this does not happen. Okay, does this make sense? Any questions on this? Okay, cool. And this is the picture that I made for the more general setting, which is that the boundary is here. The boundary is a boundary that has two parts. One of them is with multiplicity 2, which is this one here. And then there is a part with multiplicity 1. So that this at the wire there is no boundary. And the construction of the singularities that also applies for the nonlinear setting does not rely on calibrations. It relies on this kind of argument that I sketched. And a key technical ingredient is Armstrong's frequency function, which is that the frequency function captures the degree of homogeneity of the function at a point. If the function is constant, and if this function of the radius is constant, then the function is homogeneous. And in the setting that I'm considering, the points, some of the singular points actually have a property which is that they need to, a characterizing property is that this frequency needs to be at least 1 plus alpha. And then this graph is usual if one wants to get the dimensional estimate by using kind of more classical upper semi-continuity and dimension reduction. So if you're familiar with what this means, then you can actually do this using a classical kind of Federer dimension reduction. But we actually get something finer, which is that we can get rectifiability, and the estimate looks something like this, which is that for any measure which is supported on the singular set, the frequency gap is actually, there should be, okay, I didn't put where you're integrating, but it should be like on a ball of like comparable size. And then this left-hand side is measuring the flatness of this measure. And then on the right-hand side is measuring how close the function is to be homogeneous at points of the measure. And this type of the estimate is due to Neighbor and Valtorta. And for the setting of multi-valued functions, it's due to the Lellis Marquesas Paradaro Valtorta. And the quantitative rectifiability result that shows that a statement like this implies rectifiability was done both by Asamtosa and by, okay, yeah, and Edel and Neighbor Valtorta, or there is, I think you did it also prior in the work with Valtorta.
The Asamtosa assumes things that you can't assume. Assumes things like finite entrance.
Okay. Okay. Yeah, I'm trying to sketch, but yeah, okay. Okay, so the theorems of the thesis are the following for the more general setting, which is that the blowups are unique at density Q boundary points. They are a union of half planes with multiplicity meeting at the common spine, which is the tangent to the boundary. And we get a regularity theory for this class, for the class of density Q over 2 boundary points, which is that the dimension is at most n minus 3 and is rectifiable. In the case of dimension 3, we get that the singular set is countable. And without the density assumption, we also get that the regular set is open and dense. And again, this is sharp if you're considering the particular definition of regularity that I showed many slides ago. Like, if you're considering these points to be the regular points, then this is sharp for the open and dense case in the dimension. So and okay, so in general, if you put like a convexity assumption, the assumption of the convex barrier, then this density condition is true for every boundary point. And these theorems hold in this setting. And I also have the example that I sketched to you, in which you actually have a minimizing surface, which is 3-dimensional in R5, and at the multiplicity 2 boundary, it has a density 1 boundary singular point. And the singular example comes from like a curve of like branching singularities, which are kind of like, in a sense, like the complex square root topologically. And then, okay, I was moving too fast, but any question about the statements of the theorems? So the last thing that I wanted to talk about is a result that I have with Camillo on rectifiability. So for this, I need to define what a rectifiable set is. And a rectifiable set is a geometric structure that generalizes smooth embedded submanifolds. And a set is K-rectifiable if up to a set of K-dimensional measure 0, you can decompose it into countably many K-dimensional submanifolds. And what we prove with Camillo is that if you have a compact subset such that, let's say, every compact subset with finite K-dimensional measure is rectifiable, then it has sigma finite measure and is rectifiable following the same definition. And if you are familiar with what purely unrectifiable means, then an alternative way of formulating is that if you have a set whose measure is non-sigma finite, then there exists a subset with positive and finite measure, which is purely unrectifiable. These two statements are equivalent. And we were also interested. So this was done by Vesikovic in the plane in the 2-dimensional plane for 1-dimensional sets. And one of the reasons that we were interested in this was that at the technical level, it does provide some technical simplification of the Neighbor-Valtorta technique, but we do get a slightly weaker conclusion, which is that we are not able to get that the singular set has finite measure using this result. But we are happy because this allows you to get rid of sometimes nasty coding arguments. Yes. So if I can explain what?
if compact is necessary.
No, I mean, I was just being like, so our theorems hold for like, so it's more than for Suslim sets. So it's like more than Borel. So if you look at, yeah, more than Borel. So if you look at any book that has anything that requires measurability, this is like the you're not needing more than that in anything. Okay. So I think that's it. So I do want to say like some words. So this is a picture with Camillo, who I want to thank. That he advised my thesis and he got me into these problems, and he has been a great mentor, and I appreciate him for bringing me into this world and guiding me into this thesis. Then these are collaborators of mine. Part of the thesis was joined with Reinaldo Resende, who, I mean, like we work great, and he's a great friend of mine. Then this is with Xavier Tolsa and Michele Villa, and we also did some work which is not part of this thesis, but I still did it during my PhD. And then this is when Michele came to visit me with Anna and Paul, who are also like very relevant, because I mean, like they've worked in the same things. I've talked with them a lot. So I think that's everything that I have to say. But this is like the extended version of the previous one. Okay, no, I mean, okay. Yeah, okay, it's a heuristic. It's not, I mean, I don't prove that. I prove instead that what they said, which is that the normal derivative needs to have like a topological singularity. Yeah, I mean, like, okay, maybe it's like, it's slightly like misleading. But okay, it's misleading. But it's not, this is the right heuristic, but it's not like I'm explicitly proving this. It's probably correct, yeah.
Probably correct.
So
Probably correct, but we can't prove that it's exactly doing that. But
yeah,
probably the minimizer is just like, one homogeneous, and it's just simply having this branching singularity which disappears over there. I mean, that is the.
But also
proving it looks that.
But also I think at least for the linear problem, I do think that there is a way of. I mean, I in a sense I would expect that. I mean, you know that the thing is regular. I know that the thing is regular here. So in this part of the cylinder, it does actually need to be. If I restrict to slices, then I also need to see something which is topologically non trivial. So let's say if you knew that this guy was continuous, if I knew that it was continuous, all the way, I mean, like in a neighborhood of this disk, then I would know that to be correct. And I think this is, yeah. I mean, I didn't explicitly write this down, but I think, I mean, yeah, this should be correct. Yeah.
Yes, the answer, but tell me anyway to see if I'm understanding.
Yeah.
So I'm imagining there's a connection between the fact that we're studying a lot, it's more supposed to be two values.
Yeah.
And your codimension 3 that appears later. Like they did two, did one, did the other. Is there any connection? I mean, why two values?
Because it's the first example which is not one value. It's not. It's not.
But the exam, the theory is valid for everything.
The theory is very.
Yeah.
The theory is very.
Yeah.
The theory is.
The hard one, opposite, it's just two values.
Just because it's chosen.
Just because.
No, I mean, yeah. So I chose it. No, I chose it. No, I mean, I chose it to state it in this way, and then okay, how I wrote it down, in the thesis, I wrote it down for multiplicity too, but I mean, like there is no reason for. I mean, it's just like I was just happy to write it in this way. Yes. Yeah. So there are two ways. One is using like intrinsic theory of metric spaces in a way. I mean, like this is a metric space with this metric. And the other way is that you can construct a by-Lipschitz embedding that actually preserves this quantity. And if you can use the by-Lipschitz embedding and use kind of like more classical Sobolev theory to define this, if you want. And so a by-Lipschitz embedding of this metric space into some R k or some k sufficiently large, yeah. Yes. Yeah. Yeah. I mean, you can take a product. So if you take a product with some RK, then you still get something, which is area minimized. Yeah.
Okay, there are no other questions. I have to ask you folks to actually